may have heard about called AGDA. The problem I'm talking about is actually a problem I encountered while working on AGDA, but it also can also encounter it in other dependently typed languages such as Coq or Haskell nowadays. Yeah. So what's the problem I'm talking about? Well, let's take an example, and I apologize to the people who were at Tidy for this example. They may have seen it before. So the example is vectors. So these are length indexed lists. And it has two constructors. So one for the empty vector of length 0, and one for prepending an element to an existing vector, increasing the length by 1. So one of the main features of AGDA is dependent pattern matching. So this allows us to define functions on index data types such as this. So for example, we may want to define a type-safe tail function that only works if you give it a vector which has length at least 1. So in AGDA, this works by starting by giving a skeleton like this, and then doing a case split on the argument axis. So you would expect that you get two cases since there are two constructors. However, in each of these cases, there are some constraints that are generated in the background. So in the first case, we know that the length must be equal to 0. In the second case, we know that the length must be equal to suc_n. So AGDA goes ahead and solves these equations for you. So what you end up with is not these two cases, but only the single case for the cons. This is very good because we don't ever want to take the tail of an empty list. We wouldn't know what to do anyway. And moreover, in this case, we see that first argument of this cons has actually been specialized to, so we have learned that it must be equal to k. This is also very fortunate because now we know that the length of axis is equal to k, and we can just give it as the result of this function. So this dependent pattern matching is very nice, in particular that AGDA solves these equations for you. But how does it do so? Well, the answer is in the title of this presentation. It does so by applying unification to these problems. And the main problem with this is that any change in the output of this unification algorithm can change the notion of equality that AGDA has. So if there is a small error in the unification algorithm, then this can affect the whole theory of AGDA, possibly even making it inconsistent. So the main question I'm asking in this talk is how to make sure that the output of this unification algorithm is really correct. And to appreciate the difficulty of this problem, we have to zoom out a bit and look at different flavors of type theory that we want to work with in AGDA. So the basic theory of AGDA consists of, well, basic dependent functions and data types and universe, so a set. And then you can add additional axioms or primitives to that theory depending on which area you're working in. For example, you can add the excluded middle, which gives you, and another axioms, which gives you classical logic. Or on the other hand, you can add homotopy primitives, such as the univalence axiom, or higher inductive types, which gives you homotopy type theory. However, you cannot mix two of these flavors because the axioms introduced by each are incompatible. And one of the main design goals of AGDA is to work with any of these flavors. So we don't want to commit to any specific of those. Now, there is actually a third group that I like to call the syntactic group, or the syntactic flavor. And this is basically consists of all the properties that are true in the syntactic model of type theory. So for example, what we would find here is that two types that have a different name are always distinct, even if they are isomorphic. So clearly, this is incompatible with the homotopy type theory interpretation. But it turns out this is also incompatible with the law of the excluded middle, for example. So in general, these syntactic properties are something we usually want to avoid. We certainly don't want to bake them into our theory. However, if we apply a naive unification algorithm during the pattern matching, this means that we make implicit use of these syntactic assumptions, which is bad because then we cannot, it's incompatible with other axioms we may want to add. In other words, we want something, a unification algorithm that works for all possible flavors. To do so, the main idea in this talk is that we demand internal evidence of the unification process. So this means that the unification algorithm will return a term in type theory that witnesses the correctness of the unification output. And this means that we can check this proof of unification for any assumptions that are required by the unification algorithm. And the form of this evidence takes is the form of an equivalence. So this is really the type theoretic notion of an equivalence. So this means we have a function from the left to the right type and a function back, and these functions are mutually inverses. So So this is the basic idea of the talk. So the rest of the talk is structured like this. So first I'm going to explain why is the good idea to represent the output of a unification algorithm as an equivalence. Next I'm going to see explain how do you construct these equivalences and how do we make a unification algorithm that does this. And finally, we're going to extend this a bit to see what happens if dependently typed terms themselves become the subject of unification, because there's some interesting things going on there. So let's start with the beginning. The basic things we're going to do, we're going to walk through all the basic theory of unification and just translate each concept into type theory so that we have an internal representation of it. So let's start with what is a unification problem. So a unification problem, well, it consists of some free variables. And well, since we live in a typed world, they all have a type. So this is context. And then a number of equations between terms. So internally in type theory, we can represent this as a telescope containing first these variables in gamma and then the equations. So for example, we may have the telescope containing two variables k and n, and then the equation suc k equals suc n. Notice that, well, we have the bar above these u and v, so this means that we can have multiple equations. Also notice that we give a name to each equation. So in this example, it's E. This allows us to refer easily to these equations and will also become important in the third part of this talk. So we can represent unification problems as telescopes. Next up, what is a unifier? So a unifier classically means that we have a reduced context gamma prime plus a substitution that makes these equations become true. So again, how do we represent this in type theory? Well, we can represent it as a telescope map. This is just a function between two telescopes. So from gamma prime to the extended telescope gamma and E. So this means this function not just returns the values of the variables in gamma, but also proves that these equations are actually true under this substitution. And again, for example, we may have, gamma prime may be empty, and we may just solve the equation n is 0 by assigning, 0 to n and reflexivity to the proof E. Finally, usually unification algorithm, doesn't just look for any unifier, but we want the most general unifier. So what's the most general unifier? Well, it means that if f is a unifier, then it's the most general one. If for any other unifier f prime, we can find function h such that f prime equals h after f, or f after h, sorry. This is, well, we could just translate this definition into type theory, but it's not very practical. So instead, we ask that there is a right inverse to this function f, so we call it g1. And this allows us to construct the function h always by just composing f prime and g1. This means that we don't need the function h. Usually it's also required that the function h not just exists, but it's also unique. And for this, we additionally require that the function f has a left inverse g2. This may be the same as g1, but doesn't have to be. And so if we have this g1 and g2, we can actually forget about all the rest. And we end up with a function f which has a left and a right inverse. So if you know any type theory, then you may recognize this as exactly the definition of an equivalence. So we can conclude that most general unifier is an equivalence between this telescope and a reduced telescope gamma prime. And yeah, this is very nice because we have a lot of theory in type theory dealing with equivalences, so we can just reuse all this theory to work with these unifiers, or most general unifiers. So the next question we have to ask is, how do we actually construct these unifiers? And the answer is, well, we will construct them by composing basic unification rules, which also take the form of equivalences. So, for example, we may have, well, again, this simple unification problem. And one unification step may say that this telescope is actually equivalent to, well, one where we simplify the equation. This is called the injectivity rule for successor. And the next step, well, we may solve this equation since both sides are variable. We can solve for n equals k, for example, and we just end up with the single variable k. And now the most general unifier from the top to the bottom is just constructed by composing these two equivalences. Since equivalence is a transitive relation, there is no problem there at all. So what are those basic unification rules that we can use to build these equivalences? Well, the first one, very basic one, is the solution rule. So this just allows us to solve an equation whenever one side is a variable that doesn't occur in the other half. And just, well, it removes the equation together with the variable. Next up, there is the deletion rule. So this allows us to remove reflexive equations, so if the left and the right-hand side are equal. But there's actually a problem here. If we want to construct this term deletion as a term in type theory, then we notice that we need the principle of uniqueness of identity proofs in order to construct this. And this is actually one of the, So this is one of the main advantages of this approach, because it makes explicit the use of which additional axioms we need to construct these unification rules. So next there is also the injectivity rule, which just simplifies an equation between two equal constructors of a data type. And finally, there's two more rules which detect absurd equations. So there's the conflict rule, which can be applied if there's two distinct constructors. And it's encoded as an equivalence, not with another telescope, but with the empty type bottom. This is a way to represent these absurd equations in our framework of equivalences. And there's additionally also the cycle rule, which can be applied when there is a cyclical equation. So for example, n equals suc n. Okay, so cool. Now we know how to construct these equivalences by just composing these basic ones. So are we done? Well, no, of course not, because we're still working in a dependently typed language. So we also have to consider dependently typed stuff for unification. So for example, consider the type sigma A So this is the type of pairs of a type and an element of that type. So for example, an element of this sigma type is n, 0, or another could be bool, true. So if you want to simplify this equation, then we end up with one equation's n equals bool, and the second equation is 0 equals true. But now I don't know what to write here, since, well, the type of the left and the right-hand side are different. So this is called a heterogeneous equation, and yeah, so I don't really know what to do here. One solution is to use heterogeneous equality introduced by Conor McBride. But this actually causes a lot of problems when you use it, because it loses information from the unification problem. And to see this, consider the following two unification problems. So the first one is an equation between bool, true and bool, false of this sigma type we had before. And the second equation is exactly the same one, except the type here is a non-dependent product. And if we were using heterogeneous equality, then both these equations would simplify down to the same set of equations. We wouldn't see the difference. However, this equation is actually provable if you assume the univalence axiom. On the other hand, this equation is false in any version of type theory. So we really do want to distinguish between the two, and heterogeneous equality doesn't allow us to. So what we do instead is use telescopic equality, and this means that we keep track of the dependencies between the equations by introducing a new variable for each equation and allowing this variable to occur in the type of the subsequent equations. So for example, we can have the first equation between not and bool, and then the second equation between 0 and true has type this equation. So this allows us to keep track very precisely of the dependencies, and in particular, it allows us to see when an equation becomes homogeneous again, because heterogeneous equality didn't allow us to do that. So there's an additional advantage of using these telescopic equalities, and this is for the injectivity rule for constructors of index data types. For example, for example, we may have an equation between two conses of the vector constructor, and we see that the type of this equation depends on the first equation here, on E1. And then the injectivity rule for the cons constructor allows us to solve both these equations at once. So not just the equation between the constructors, but also the equation between the indices of the data type. And we just end up with three equations between the three arguments of this cons constructor. Now, this may not seem very impressive if we do it here, but actually it increases the power of the unification algorithm by quite a bit. To see this, sorry, my clicker is, to see this, consider this data type image, which, well, basically image fy consists of all the elements x such that f of x equals y. So that's what the image constructor says. The index here is f of x. And then if we have this unification problem here, so we have two equations, one between the indices and one between the two constructors, then we can again solve both the equations at once. And well, notice that this equation, otherwise we wouldn't be able to solve it because we don't know anything else about the function f. So this really turns unsolvable problems into solvable ones. We can. So there's a few things in the paper that I didn't mention. So the actual construction of these unification rules as terms. There's, well, of course, these terms as terms of type theory, they also have a computational interpretation, but I didn't talk about them. There's additional unification rules for record types, and also a number of reverse unification rules, which are used to apply this injectivity rule in more general situations. But it's actually outdated. I have a new version of it which I will talk about soon, maybe at a different place. And finally, all of this has been used in the implementation of Agda for the implementation of the dependent pattern matching. Yeah. So to conclude, what have we done? We have given a new definition of the most general unifier internal to the type theory. That is, well, it's guaranteed to be correct by construction. So it can never go wrong. And also, these terms can be used directly in the compilation of dependent pattern matching down to eliminators. That's it. Thank you.
Thank you. Questions? Simon?
So this is very interesting, and you probably know it's quite similar to what happens inside GHC for evidence passing. But I was wondering, just on this last slide, when you say it's correct by construction and cannot go wrong, I regret to say that it is possible for GHC to go wrong sometimes, but the sort of the type checking of the proofs can, as it were, serves as a belt and braces, so we can check whether the type checker has gone wrong. Is that true here? In what sense can you not go wrong in a complex type inference algorithm?
So the way it can not go wrong is that all the unification rules we have actually are backed by evidence, which is terms in type theory. So of course, if one of these terms is not type correct, then it can go wrong. But assuming that this evidence is type correct, then there's nothing else that goes wrong.
There you go. So you have an internal check in which you type check the evidence to make sure it's okay, do you? Just hope.
Yeah, so currently the implementation doesn't actually produce this evidence, so it's mainly a proof on paper that the unification rules are correct. Yeah. Okay,
GHC actually produces the evidence and actually checks it.
Okay. Yeah, we should do that, but it's not implemented yet. Yeah.
So many. Yeah. Actually. So in the classical unification, sorry, I'm Stephen Dolan of the University of Cambridge. In the classical unification, the output of unification is usually proved to be the most general idempotent unifier rather than just the most general unifier, because the most general unifier, there are most general unifiers which uselessly permute variables. So I'm wondering why idempotence doesn't show up in this.
Okay, that's a good question. I'm not really, wait, so yeah, something. Talking about this picture. Yeah, so you're saying you could have a permutation of gamma prime and it would be a different most general unifier. So yeah, it's true that we can have multiple most general unifiers, but they are all, I mean, in a sense, equivalent. And it doesn't really matter in which order these variables are because it's never, I mean, it's never shown to the user. It's just something that goes on behind the scenes. Yeah. So we just take any order of the variables in gamma prime.
I'm afraid we have to take the rest of the questions offline. Thank you again.